1. What is a mineral? The Earth's crust is composed of about 3,000 different minerals that play important roles in the forming of rocks and in the shaping of Earth's surface. A mineral is a natural occurring, inorganic solid with a specific chemical composition and a definite crystalline structure. If you look at the pie chart on the left, you see the most common elements in the Earth's crust. Oxygen being 46.4%, followed by silicon, aluminum, iron, calcium, sodium, magnesium, and then small bits of potassium, titanium, and hydrogen. On the right, you see some samples of minerals that we're going to be talking about. Definite crystalline structure. The atoms in minerals are arranged in regular repeating geometric patterns that result in the formation of a crystal. The crystal on the left is a pentagon crystal because you see each one of the sides is a 5-sided pentagon. On the right, the crystals are more cubic, so they're more square, but you're seeing it under different forms of ultraviolet light, which show one of the specific things of certain crystals. They will glow under ultraviolet light. A crystal itself is a solid in which the atoms are arranged in repeating patterns, and you see that both in the crystal on the left and the one on the right. Rock-forming minerals. There are 8 to 10 of the most 30 common minerals are referred to as rock-forming minerals because they make up most of the rocks in Earth's crust. Rock-forming minerals are primarily composed of the 8 most common elements in the Earth's crust. The first one we're going to look at is silicon dioxide, which is quartz. The second one is feldspar. The third, mica, pyroxene, amphibole, olivine, garnet, and calcite. They all have different colors, they all have different structures, they all have different crystals. But what they all have in common is these 8 most common elements are in their formulas. So if you look at their formulas and you look back at this pie chart, you will see that those are the elements that make up the most common elements that are in the rocks of the Earth's crust. Now, there's different ways to form rocks. The first one is molten rocks. Minerals from magma are formed by the accumulation of magma underneath the Earth's surface. What you're seeing here is lava. When it comes to the Earth's surface, it turns into lava. Underground, it is magma. Now, the magma is less dense than the surrounding rock, so it can go upward in the cooler layers of the Earth's interior, where it cools and crystallizes. If it crystallizes on the outside, it will form one form of rock. If it crystallizes underground, it will form different forms of the same rock, but different crystal structures. The type and number of elements in the magma determine which minerals it will form. The rate at which the magma cools determines the size of the crystals. Small crystals form from rapidly cooling magma, and large crystals form from slowly cooling magma. The rapidly cooling magma would be the ones that reach the surface and are cooled by the air. The slower cooling magma are under the surface, and over time they slowly crystallize, so you get much larger crystals. And here are some examples of crystals that are formed. You can also get minerals from solutions. A liquid is a saturated solution when it becomes fully dissolved with a substance that can no longer dissolve. On the left, you see what we call a supersaturated solution. It is when there's more minerals dissolved in it than should be, and all it takes is a small seed, a piece of dust, a shaking of the flask, and it will start to crystallize because the supersaturated will become saturated and the crystals will form. So what happens on the left side is shown almost in regular time. It is not time-lapse. It is that quick that the crystals can form. On the right side is the opposite. Those are evaporites. Evaporites are formed when the liquid that it's in, that it's dissolved in, will slowly start to evaporate, and the crystals will form as the water evaporates. Those are called evaporites. Identifying minerals. That's what we want to do in this chapter. Geologists identify minerals using tests based on their physical and chemical properties, mostly physical, some chemical. First is crystal form. Some minerals form distinct crystal shapes and they are immediately recognizable. However, perfect crystals are not always formed, so identification based only on crystal form is rare. On the left side, that is a mineral because it's got a mixture of different forms, where on the right side, that's a crystal because that is one element that is formed and it is very recognizable. The way a mineral reflects light from its surface is called luster. There are two types of luster. Metallic luster, like we see here, with the metal ores of copper, silver, gold, and iron. This is how they're naturally formed. They're found in the ground with other elements attached to them. That's why they're called ores. Luster can be metallic, like these four, or it can be non-metallic. The non-metallic lusters are more prevalent. You will see a lot more minerals with non-metallic lusters than metallic lusters. And here are some of the examples of those lusters there. Luster can be used in combination with other physical characteristics to identify a mineral. You don't usually just use its luster to identify it. Hardness. Hardness is a measure of how easily a mineral can be scratched, as you're going to see in a second. German geologist Friedrich Mats developed a scale by which an unknown mineral's hardness can be compared to the known hardness of 10 easily recognized minerals that, with the exception of diamond, are readily found in nature.
How can I determine the hardness or the ability of this mineral to resist scratching? It's the Mohs scale to the rescue. The Mohs scale of mineral hardness is based on the ability of one mineral to scratch another mineral visibly. The Mohs hardness scale was developed in the 1800s by Friedrich Mats, a German mineralogist. Hardness is a measure of a mineral's ability to resist scratching. He selected 10 minerals of different hardness that range from a very soft mineral like talc to a very hard mineral like diamond. Mohs hardness is a measure of the relative hardness and the resistance to scratching between minerals. When doing the test of minerals, it's necessary to determine which mineral was scratched. Let's go through the Mohs scale. As you move up the scale, hardness increases. At number 1, talc. 2 is gypsum. 3 is calcite. 4 is fluorite. 5 is apatite. 6 is feldspar. 7 quartz. 8 topaz. 9 corundum. And then the hardest is a diamond. You can also use common household items to test for hardness. For example, a fingernail has a hardness of around 2 to 2.25. A penny is between 3 and 3.5. A nail, 5 or 6. A piece of glass, 5 or 5.5. A streak plate, around 6. And a piece of quartz, around 7. Let's determine the hardness of this mineral. First, it can scratch talc, which I know is at 1, so it's greater than 1. But it can be scratched by calcite, which has a hardness of 3. So it has a hardness of 2. This fact helps me identify the mineral using a simple chart as gypsum. If you'd like to know more about the Mohs hardness scale, this playlist will help. And as always, thanks for watching, and Moo Math uploads a new math and science video every day. Please subscribe and share.
Now, you have a Mohs scale of hardness, and he went from bottom to top. We're going to go from top to bottom. This is the same scale that he was just talking about, and there are the examples: talc, gypsum, calcite, fluorite, apatite, feldspar, quartz, topaz, corundum, and diamond. So you can see examples of each of those. Now you have a worksheet where I'm going to ask you some questions about Mohs scale. You don't have to memorize it, but it's a good thing to have handy if you're trying to identify elements by their hardness. Cleavage and fracture. A mineral that splits relatively easily and evenly along one or more planes of weak bonds is called cleavage. On the left side, you see him breaking the calcite, and it is breaking in a nice straight line, so that's considered a cleave, or cleavage is a straight line break. To identify minerals based on its cleavage, scientists count the number of cleaved planes and study the angle or angles between them, because it will always be the same, because minerals are always made of the same elements. Minerals that break in a rough arc-like or jagged edge because of their tightly bonded atoms are called fractured. On the right side, you see a fractured surface because it's not straight like the one on the left. It's all arced and odd. And that's why you would say that's a fracture versus a cleave. Now, you have Mohs hardness scale. And we've already talked about what works with which, so I have some questions for you. Number one, what is the property of mineral hardness measure? It measures how easily a mineral can be scratched. Number two, what is the softest mineral shown and what is its hardness? Well, I look at the top where it says softest, and that would be talc, and talc is considered 1. Number three, what is the hardest mineral shown and what is its hardness on Mohs scale? So I look at the bottom where it says hardest, and I believe that is a diamond. So my answer for that would be diamond with a hardness of 10. Number 4, explain how you could estimate the hardness of a mineral that does not appear on the scale. Well, if it wasn't on the scale, what I would have to do is I'd have to estimate. So I'd have to compare the hardness to known minerals. So if the mineral can scratch calcite, which is a 3, but cannot scratch apatite, which is a 5, the hardness would be somewhere between 3 and 5, because it can scratch a 3, but not a 5. Number 5, which common object will scratch feldspar? Feldspar is a 6, so I would have to use a steel file, which is 6.5, because anything harder would scratch it. So my answer to number 5 is I would use a steel file. Number 6, which minerals on Mohs scale will scratch apatite? Which will apatite scratch? Well, the ones that are going to scratch apatite are these. You look at it and it will be scratched by anything harder. So feldspar, quartz, topaz, corundum, and diamond, but it will scratch talc, gypsum, calcite, and fluorite because they are lower in Mohs scale. And last but not least, number 7, what is the hardness of a mineral that scratches gypsum but cannot scratch calcite? So I look here, gypsum is a 2, calcite is a 3, so it would be somewhere between 2 and 3. So I'm going to say for number 7, the mineral scratches gypsum, so it's harder, which is 2. If it cannot scratch calcite, it's softer than a 3, so it's somewhere between 2 and 3. Streak tests are another thing. Streak is the color of a mineral when broken up and powdered. The streak test, which typically involves rubbing the mineral against an unglazed porcelain plate, is often used to identify metallic minerals. It can be used only on minerals that are softer than the porcelain plate. And the weird thing about it is sometimes you will rub a crystal that's one color and it will streak a totally different color. And that's something that's important in identifying minerals. Color. Color is one of the most noticeable characteristics of a mineral. It is also one of the least reliable clues of a mineral's identity. If you look at all of these different examples, they all have different colors, but some of them are kind of close. If I look at the white opal, and then I look at the marble, and then I look at the talc, they're all white. So color is not the best way to identify it. Because if I just tell you it's white, there's a lot of different things that are white. Same thing, there's a lot of things that are green. There's a lot of things that are violet in color. So that's not the best way to identify. Several special properties of minerals can be used to identify them also. Some of these properties are magnetism. If you look at the first one, the man's bringing the piece near it, and because it's a compass, it will then be attracted because that is a magnetic sample. A second one is iridescence. Iridescence is when it will give off light and it will actually give off different colors. And as you see this spinning, it goes from one color to the next. Another one is double refraction. Calcite is a type of mineral that will have a double refraction. As you're looking at it, it looks like there's actually two different things of calcite. That's called double refraction. Another one is effervescent. If you take a weak acid and you add it to certain minerals or certain rocks, it will start to bubble and it effervesces. It gives off bubbles because it's got carbonates in it. So that's carbonation. It's carbon dioxide that's being given off. And last but not least is fluorescence. Fluorescence is a neat thing that when you look at certain things under different wavelengths, they give you different colors, and that's called fluorescing. Texture. Texture describes how it feels to the touch, and like luster, it's very subjective. It's often used in combination with other tests to identify a mineral. If you look at these, some of these definitely look like minerals, but others don't look like minerals because you would probably feel them and they would feel chalky, or they would have a feel of like rough grass or something like that. So that's not the best thing. Density and specific gravity. Density reflects the atomic mass of the structure in the mineral. The most common measure of density used by geologists is specific gravity, which compares the density of the rock to the density of water of equal volume at 4 degrees Celsius, because only at that temperature is water's density 1. So then they can compare it with that, and every element has its own density. And then if you know a lot about the different structures, you can then identify which elements are in there by its density. Mineral groups. In order to study the many minerals and understand their properties, they've classified them into groups. Each group has a distinctive chemical nature and specific characteristics. One of the most common types are silicates. Silicates are minerals that contain silicon and oxygen, and usually one or more other elements, and those are called the silicates. All below, the feldspar, the mica, the olivine, the quartz, and the pyroxene are all silicates. Silicates make up about 96% of the minerals in the Earth's crust. The basic building block of a silicate is the silicon-oxygen tetrahedron, which you see on the right side. A tetrahedron is the plural, being tetrahedra, many of them, is a three-dimensional shape that resembles a pyramid. So silicates are going to have that pyramid shape, which is going to then help shape the minerals themselves. Because silicon can have 4 valence electrons, which gives it 4 bonds with oxygens. As you see with the ball and stick, I have the silicon in the center and 4 oxygen ions around it, or the space filling, which is more realistic because the atoms are not that far apart, shows the same thing. It is called a tetrahedron. Silicates. Individual tetrahedron atoms are strong and can bond together to form sheets, chains, and complex three-dimensional structures. And you see them on the right side. You see the different forms. The bonds between the atoms help determine the cleavage or if it's going to fracture. So we have 3 different types there. We have pyroxene, which are single chains of tetrahedrons. We have double chains with the amphibole. And we have sheets of tetrahedrons, which is mica. Now, to visualize this, the silicon-oxygen tetrahedron contains 4 oxygen atoms bonded to a central silicon. The chains, the sheets, and complex structures form when the tetrahedra share oxygen atoms. These structures and the type of metal ions that are bonded to them will determine the different silicate minerals that are present. So the pyroxene and the amphibole and the micas all have different metals in them that help to form the chains, the double chains, the sheets. Carbonates are the second one. Carbonates are minerals composed of one or more metallic ions and the carbonate ion, which is CO3 with a -2 charge. Calcite is an example. It is actually the formula is calcium carbonate, CaCO3. Oxides are compounds with oxygen and a metal, such as hematite, which is right here, which the formula for hematite is Fe2O3, which is the same formula as rust. The difference between hematite and rust is this is one that naturally forms underground and on the ground. It is not iron that has been oxidized. It's iron that's been oxidized by nature, not by exposure. Other groups, sulfides. Pyrite on the left is iron sulfide, FeS2. That's what they call fool's gold. People used to think that they would get this and it was gold, and people would sell it as gold, but then when they did the density test, the specific gravity test, the density of gold and the density of pyrite are not even close. So if you feel a piece of pyrite, it will feel like a lighter rock versus a piece of gold, which is a heavier, denser mineral. Sulfates are common compounds of elements with sulfur and oxygen. The sulfate ion is SO4 2-. The anhydrite that you see on the right is calcium sulfate, which is different from any other form. Halides are made up of chloride or fluoride along with calcium, sodium, or potassium, such as the halite that you see below. We would call that rock salt. Native elements are made up of one element only, such as the piece of silver that is listed there on the right side. Ores, economic minerals. A mineral is an ore if it contains a substance that is profitable. For example, if you look at the left side of the first diagram, it shows a mineral versus an ore. On the left side, you have pyrite. On the right side, you have gold ore. Classifying minerals as an ore can change if the supply or demand changes. So if something is very valuable, it's considered an ore. If it's not, it's just a mineral. Ores that are located deep within the Earth's crust are removed by underground mining. Those near the Earth's surface are obtained from large open pit mines. The removal of unrotted rock and dirt from mining can be expensive and harmful to the environment. So they have to weigh the difference between expense and profit. The last one is gems. Gems are valuable minerals that are prized for their rarity and beauty. Such gems as rubies, emeralds, and diamonds are cut and polished and used for jewelry. As you look down there, you see several types of minerals that are considered gems because the gemstones are then used in jewelry.